about ions and how they behave in aqueous solutions. And what does aqueous mean? Aqueous means a solution with water. So if we look at that word aqueous, there's that root aqua, which is Latin for water. You can think about the Spanish, in which water is what? Agua. So those are all related terms. So aqueous specifically refers to a solution in water. That's important. Now, can we make a solution with some other liquid? We can. We don't do it very often. Water is a universal solvent. It's very good at dissolving a lot of different things. So it is very useful, and it's the thing we use most commonly to make solutions. Okay, so an aqueous solution is one with H2O as the solvent. Okay, so here we have our chunk of sodium chloride, and we've got all these ions, and they are all held, every sodium is held in attraction by all the chlorines around it and repulsed by all of the other sodiums around it. So it's got this very strong set of bonds that are holding it all together. They're not actually physical shared bonds like with a molecular compound. They're just very strong bonds of attraction. So if we put this stuff into water, what's going to happen? There's our little Mickey Mouse water molecule. So one of two things can happen. A lot of you said break up, and the water could break the sodium chloride up into smaller chunks. Could break it up into smaller chunks of sodium chloride. Do you think that's what happens?
No.
Yes and no. Good, good, good. I want to hear dissension in the ranks. I like this.
I'm going to say no.
Okay, so that's one possibility. The other possibility is that this water actually gets in between each of these individual little ions and separates them out.
I like that one better.
You like that better? That every little ion gets herded off by itself, like a little lost calf? Okay. Well, interestingly enough, dissociation is the process whereby water molecules separate all the ions in an ionic compound. Because if you remember, water is polar, which means these areas up around Mickey's ears that have a partial positive charge can circle around these chloride ions and surround them. And the chloride ions find Mickey's ears pretty darn attractive and will form a little sort of huddle where you have a chloride ion in the middle and a bunch of Mickeys hanging out around the edge, just sort of gawking at the very attractive chloride ion, Mickey's ears. Well, the chin, the bottom of that oxygen, has got a negative charge. So the sodium ions find that pretty attractive. So we get sodium ions with a bunch of little Mickeys hanging out around with their chins pointed at sodium. This is dissociation, and this is the image that's shown in your notes, where those water molecules, those are molecules, separate and surround all of the ions. And now the ions are no longer really part of a compound, though we still treat them as though they are. We actually write an equation for this happening. It is not a chemical equation, it's a dissociation equation or ionic equation. So we're going to show that right now. So far, what this shows is that we have solid sodium chloride, and the H2O over the arrow means it is dissociating in water. So what we're going to draw next are the ions that it breaks up into. What we have to do is we have to list their state. What state are these sodium and chloride ions in? They're in an aqueous solution, so they get an AQ. Okay. Now, when we're doing an ionic equation, a dissociation equation, some of the things we have to pay careful attention to. We still have to balance this like we did chemical equations. So we have to have the same number of atoms of each thing on each side. Well, we've got one sodium, one chloride, one chloride. That works. The other thing we have to pay attention to, now this side will be neutral, because these are not charged particles. These are compounds. But over on this side, we have charges to deal with, over here. So here we have 1 plus, 1 minus. They have to be equal but opposite, okay? So these have to sum to 0. If they don't, you have to do some adjustment, and we're going to do one like that in just a second here. Let's look at the dissociation of calcium chloride. Okay, so we've got solid calcium chloride being put into water. What 2 ions will this break apart into? Name me one.
Calcium.
Calcium ion. What is the charge on a calcium ion? 2 plus. Okay. What's the other ion we're going to see? Chloride ion. What's the charge on a chloride ion? 1 minus. Okay. We have to put in our state information. These are both aqueous. Now we have to look at balancing this. Is it balanced right now? No. We've got 1 calcium here, 1 calcium here. That's fine. 2 chlorides there, 1 chloride here. So we have to put in a 2 there. Now that actually goes ahead and fixes our other problem. Because before we did that, we had 2 plus, 1 minus. Well, now what we've done is we've multiplied that 1 minus by 2. So these sum to 0. Your charges have to, your charges have to balance. I know you've been missing stoichiometry, so here we go with the stoichiometry of dissociation. Yeah. If you have something that you are dissolving according to one of these ionic equations, you can actually figure out how many moles of your compound is going to yield how many moles of each ion and how many total moles of ions. So let's practice this with our calcium chloride that we just did. Okay, so we've rewritten our dissociation equation for calcium chloride, and there's a sort of invisible 1 in front of this calcium chloride. So we're talking about 1 mole of calcium chloride breaking up, right? For every 1 mole of calcium chloride that breaks up, how many moles of calcium ions will we produce? 1. For every mole of calcium chloride that breaks up, how many moles of chloride ions will we produce? 2. So, for every 1 mole of calcium chloride that breaks up, how many total moles of ions will we produce? 3. Okay, that's not that difficult, but it throws a few people for a loop. So let's practice something a little bit even more complicated. Page 426, sample problem 1 at the bottom, part C. Question we have, how many moles of each ion and total ions are produced when 0.5 moles of barium nitrate is dissolved? First of all, we need to write the formula for barium nitrate. Okay, so we've written our dissociation equation for the dissolution of barium nitrate. Breaks down into how many moles of barium ions? 1 for every 1 mole of barium nitrate. How many nitrate ions? 2 for every 1 mole of barium nitrate. That's easy. Now, we're told in the problem that we're only dissolving 0.5 moles of barium nitrate. So you want to set up a factor label. So we just show basically this is a mole ratio just like we use in a chemical equation, but for dissociation. So whatever we're starting with, the mole ratio for the dissociation, and we've got a total. So the answer to this question is when we dissociate, or when we dissolve 0.5 moles of barium nitrate, we're going to produce 0.5 moles of barium ions, 1 mole of nitrate ions for a total of 1.5 moles of ions. Okay, and you'll have some problems like that to practice with in the homework. Now, we've talked a lot about solubility, we've talked a lot about making solutions. Now we want to predict what will dissolve in water. So if you would be so kind as to turn to page 427 on your book, we are going to do some solubility prediction. So in your book, page 427 of Modern Chemistry, what you're going to find is a general solubility guidelines table. These are not hard and fast rules, they are guidelines. And for every compound that we look at solubility on, you're going to look at what's in that compound, look at the guidelines, and see if it's soluble or not. So this is our first compound, NH4NO3. What is that compound called? When we go to the general solubility guidelines table, we're going to read each rule and see if there are any references to ammonia compounds or nitrate compounds. So what's the first rule? Please, I'll read it. Most sodium, potassium, and ammonium compounds are soluble in water. Does that address the compound that we have? Yes. So far, so good. That makes it seem as though it is probably soluble. We have to keep reading, though, because sometimes there are exceptions. Number 2, most nitrates, acetates, and chlorates are soluble. Does that apply to our compound? Yes. Still saying probably soluble. Number 3, most chlorides are soluble except those of silver, mercury, and lead. Lead 2 chloride soluble in hot water. Doesn't apply. Rule 4, most sulfates are soluble except those of barium, strontium, and lead. Doesn't apply. Number 5, most carbonates, phosphates, and silicates are insoluble except those of sodium, potassium, and ammonium. It's an ammonium compound, but it's not an ammonium carbonate, phosphate, or silicate. Doesn't apply. Most sulfides are insoluble except those of calcium, strontium, sodium, potassium, and ammonium. Again, we have an ammonium compound, but it is not a sulfide. So, is this soluble? Yes, it is. And we base that on rules number 1 and 2. Let's check out our next compound. So we have 2 rules that pertain to this compound. Number 1, which says most ammonium compounds are soluble. Number 6, which says most sulfides are insoluble, except, and they've got a few exceptions. So you want to read carefully and make sure that you catch all the instances that would apply. So ammonium sulfide is soluble. Now, let's practice with CaCO3. What do we call this? Calcium carbonate. Find me a rule. Yeah, so based on Rule 5, most carbonates are insoluble, and none of the exceptions apply. This one is insoluble. Okay, so we got our first insoluble. Now, let's look at our next compound, AgCl. What is this called? Not soluble. Okay, so Rule 3 says most chlorides are soluble, but not silver. It's one of the exceptions. So this compound is insoluble. Okay, and let's look at our last one, BaSO4. What is this called? Barium sulfate. Find me a rule. Okay, so based on Rule 4, most sulfides are soluble, but barium is given as an exception to that rule. So this is insoluble. These aren't very hard to do. You just look for the rules that pertain. The place to be careful is with the exceptions. Now, why is this so important? So you know if you're not part of the solution, you are part of the precipitate. That's right. Okay, so we've talked about solutions and precipitates. We know that if we're not part of the solution, we're part of the precipitate. What is a precipitate? What is a precipitate? Pardon? No. Which means it is a substance that is insoluble. So a precipitate is made up of insoluble compounds. A precipitate is something has formed in a solution that is not soluble. And then it comes out of solution, and suddenly, presto, we go from having a nice clear solution to having some sort of muddy water. We can actually predict when 2 substances will form a precipitate. So, let me ask you a series of questions. Actually, we're going to save those questions for tomorrow, or for Monday. We're just going to do a little demo up here, but on Monday we will start talking about how we can predict if 2 solutions will form a precipitate or not. Okay? So the homework is up on the board. That homework, those few problems are due on Monday. It's got assigned due dates in chunks now, and we'll talk more about precipitates and predicting them.